let's read about what a one-to-one function is in the box here. So we say a function with domain A is called one-to-one if no two elements of A, the domain, have the same image. So what that means is if we plug in two different x values, they go to two different y values. That's what this is saying. And that's what's being shown in our classic bean pictures here. We've got our domain as A and our range as B. And you can see that everything in the domain is going to its own value in the range, and two things in the range are not being hit. I'm sorry, let me say that again. Things in the range are not being hit twice by things in the domain, right? Everything in the domain goes to one distinct thing in the range. And so that's why this graph is one-to-one, because every x value gets sent to a unique y value. That's what it means to be one-to-one. The one on the right is not one-to-one because of what? What's making this picture not one-to-one on the right? Disa?
Both 2 and 3 go to 4.
Good. Both 2 and 3 in the domain get sent to 4. And so this is not one-to-one because x equals 3 and x equals 2 are both sent to y equals 4. And so this means we do not have a one-to-one function. And so I usually like to look at the pictures first, and then I'll just write that down right up here just to be a little clear about that. So we say, this is talking about when a function is one-to-one, and I just want to be clear that a function is not one-to-one. Oh, let me introduce this here. This abbreviation, 1-1. So the way we write that out is 1-2-1. That's how we write it out in words. I like abbreviating it with the abbreviation just 1-1. Is that okay? So anyway, a function is not 1-1, one-to-one, if two x values get sent to the same y. How is this different than the definition of a function? People always confuse this with the definition of a function. Does anyone remember what the definition of a function is? So we had the vertical line test with the definition of a function. Yeah, you remember? Right. So we had the vertical line test for the definition of a function. A function says, or the definition of a function says, every x value gets sent to just one y. So what's the difference here?
No two y values share the same x.
No two y's share the same x. So it's a little bit different. So a function means that every one of these on the domain gets sent to just one in the y. In other words, what violates that is if 2 got sent to 4 and 7. That would not be a function. That's different here because this says that two separate x values go to the same y. They're slightly different. They're slightly different definitions, and so I'm just warning you, be careful with confusing the two of them. And to make things a little more confusing, on the next page you'll see we have something called the horizontal line test. And so we're going to draw horizontal lines instead of vertical lines on these. And so it's just showing a slight distinction between the two of them. So I encourage you to compare this section to the definition of a function just to make it clear to yourself. Are there questions on this concept, though? So this is why this is a good sort of understanding picture, I think. This is not one-to-one because one y value is associated with 2x. That's different than a function because a function would not be a function if it was two y values are associated with 1x. Slightly different. Okay, anyway, let's talk about how we figure out whether or not they are one-to-one. So there's two ways to determine if a function's one-to-one. Logically, that's what's on this page. You can see the first thing that we're going to talk about is logically. And then graphically, that's the next page. That's what the horizontal line test will be. So logically, what's going to make two different x values get sent to the same y? Well, usually it's because of an even power situation. So even powers are usually not one-to-one. And odd powers usually are one-to-one. Again, I'm just saying usually because it's not always the case, especially if you have a mix of them, right? If we have like x cubed plus x squared, we have both odd and even, and so then it's not exactly clear which is which. So that's why I'm just saying usually and not all the time. Alright, so let's look at a couple examples. So logically, a function that sends two separate input values, which we think of as x values, to the same output value, which we know as y values. And so you just have to think about if that's going to happen. And like I wrote here, this is usually a little bit more difficult because you have to consider all the possible values in the domain and think about whether or not they get sent to the same value. But you should use this as a guiding principle, right? If it has even powers, it's usually not, and if it has odd powers, it usually is, and use that as a guiding principle to help you think about that. So for example, is x squared one-to-one? It's got an even power, so I'm thinking it's probably not, based on my original, what I wrote down up here. And so I'm trying to think, are there two separate x values that when I plug it into x squared, I get the same thing out? Like what? So the answer is no. I'm seeing a lot of head nods there. The answer is no. But why, for example? What are two x values that get sent to the same y? Yeah?
X squared, negative 2 and 2.
Yeah. Any plus or minus version of the same number, right? So x equals 2 and negative 2 are good. X equals 2 and x equals negative 2. If we plug those into the equation, yield the same y value. Still on the screen? Yes. Leave a little room for a graph at the end there. I.e., if we plug in 2 into the function or we plug in negative 2, we get the same number out, which is 4. Because we square that number and it doesn't matter whether it's positive or negative, right? And so visually, what that looks like is this. This is what x squared looks like. It's not the best drawing of x squared, but you can see it's symmetric with respect to the y-axis. And it doesn't matter whether we plug in a negative x or a positive x. They both get sent to the same y value. In other words, things that are symmetric with respect to the y-axis are not one-to-one. That's another way to say that. Questions? You guys kind of get what one-to-one is? What about this next one? Does that equation look familiar? Anyone know what that type of equation is, what that looks like? Remember, Gaia? Yeah, good. That's a circle. That's the equation of a circle. So just thinking about what a circle looks like, is it going to be one-to-one? No, for the kind of the similar reasons as the last one, right? And so a circle is not one-to-one. And for example, I'm going to think of 2 points that I can plug in that are going to give me the same y value. So I'm thinking any positive or negative value. So if x is, say, -3, then that means that y has to be 1. And if x is +3, y is still 1. And so this is showing us two separate x values, 3 and -3, that get sent to the same y value. Right? Two x values sent to the same y. And so that's why it's not 1-to-1. And let's just draw this picture too, right? So circles look like this. And we can see that it doesn't matter whether we plug in, say, -x there or +x there. They both get sent to the same y value. So circles are also not 1-to-1. But also notice even powers, right? Even powers usually not 1-to-1. Thoughts? Is that okay? So convince the person next to you about the next one, x cubed. Is x cubed 1-to-1? So form an opinion on that. It's got an odd power, so that should tell you something, right? That's not even anymore. It's an odd power. So convince the person next to you whether you think that one's 1-to-1 or not. And say 30 seconds. And I'll draw the picture here to help motivate your conversation. Here's what x cubed looks like. We already drew a picture of that before, but here's what it looks like, right? So convince someone that this is 1-to-1 or not. All right, so is this one 1-to-1? I think it is too. Does anyone want to summarize like why, other than because it has an odd power? What is it about having an odd power that makes it okay? Yeah.
Positive and negative of the same number comes through the same.
Yeah, when you plug in positives, they stay positive, and when you plug in negatives, they stay negatives. You don't have that problem where plugging in negatives become positive. That was the problem, quote unquote. The problem with the circle and the x squared is that when we plug in the negative values, it's the same as plugging in the positive values because the even power makes it positive, right? And so we don't have that issue here. And so if we plug in a positive x, it stays positive. And if we plug in a negative x, it stays negative. And so it is 1-to-1, and we can just see it in the graph, right? Every single x value is going to go to its own y value. I can't draw a graph, I can't draw a picture like the previous two where we have two x's going to the same y's. In other words, there's not a place on this last graph where the height is the same in two separate places. The height is always different as we move left to right. But unlike the circle, the height here is the same as the height there. And the height here is the same as the height there, and all over the place on those. And so that kind of leads into the next page, which how we can see it pictorially. So before we even look at that, and maybe you already have and whatever, what is the answer? How do we know visually, I already said it, but someone else say it differently. How do we know visually if a graph is 1-to-1 or not? Jackie, do you want to say something?
I was going to say when it's not symmetric.
Well, you're right. It won't be symmetric with respect to the y-axis, for one, right? This one is not respect to, like, we can't fold this one over and it'll line up, but the other two will line up. So you're right, it won't be symmetric with respect to the y-axis. That's definitely true. What else? Anna? Yeah. When I said that, that was very good. So when I said the graph has the same height, what that means is if I drew a horizontal line through the graph, it would touch twice. And so if we can draw a horizontal line through a graph and it only touches once, that's indicating we have a one-to-one function. And that's what the next page, that's literally what it says. All right, so the way we figured these out graphically, if a function is one-to-one, then every output value, y, is achieved by only a single input. And so if we're looking at the graph of a function, that means that every y value has only one corresponding x. And so that leads to the horizontal line test, right? We only want to have every every y value associated with one x. And so a function is one-to-one if and only if no horizontal line intersects its graph more than once. So for example, I'm just going to do the first one real quick. This is an example similar to the last page. Notice we've got an even power, x minus 1 squared. So that shouldn't be one-to-one usually. And we can prove that because I can draw a horizontal line and it'll touch twice. So this is not a one-to-one function because a horizontal line touches the graph twice. All right, so which other ones are also, let's just go through them one at a time. You go through them in the next, you probably already did it, but just take a second, draw some horizontal lines, and tell me which ones are and aren't one-to-one, right? So if it intersects more than once somewhere, it's not one-to-one. And if it can only intersect once, it is. So it only takes probably a moment to think about these. All right, so is this next one one-to-one? Yeah, this one is. The next one is one-to-one, right? Horizontal lines only touch once. So I just want to make that clear once. Horizontal lines only touch once. All right, what about the next one? Is this one one-to-one? No. Even though we can draw horizontal lines up here and down here that are okay, anyone in this general region is not going to be okay, right? So we would end up hitting it more than once, and this one is not one-to-one. The next one is, because we can draw horizontal lines, it'll only touch one time. So this one is a yes, it's one-to-one. The next one's similar, right? It almost flattens out here. We almost have a problem towards the end, but it's not because it's still increasing. So we'll still only touch one time there. So this one is one-to-one. And what about the last one? No. Even though it's okay on the top and the bottom, if we draw a horizontal line, it will line up with that one and touch it infinitely many times throughout there. And so that one is a not one-to-one. Okay, I want to just reiterate this with, or kind of compare it with functions. Let's talk about functions quick, because we had the vertical line test with functions, right? And so functions say every single x value gets sent to one y. So all of these pass the vertical line test, right? We can draw vertical lines through all of these, even this one, because that's not quite vertical there, right? We can draw vertical lines through that and it'll only touch once. Vertical lines, all of these will only touch once. So, what does that mean? Are they functions or not? If they all pass the vertical line test, that means that they are or aren't functions. They are. And so what I want to note down here, and you might want to, again, you might want to just compare this to the definition of a function section to make it clear in your head. But note, each graph above is a function. By the vertical line test. Right, so the vertical line test and the horizontal line test are two different things, and something being a function is different than being one-to-one. They're very similar, and I'm standing up here closing my eyes sometimes trying to get them straight in my own head because they're a little bit confusing. They're very similar. So just, I can't stress this enough. Before you forget about this stuff, look at the function section. So these are all a function by the vertical line test, but some are not one-to-one. Okay, so there's a difference between something being a function and one-to-one. And so they're not one-to-one, just to be clear, by the horizontal line test. Two different tests, two different concepts. But very similar and very confusing, so take a look at those two, compare them. So we just finished talking about one-to-one functions in the last section. And this section is a real natural progression from one-to-one functions, which is function inverses. And so what is a function inverse? Let's start there. That's what's being shown in this box here, and I'm kind of explaining it in the paragraph above. But what a one-to-one function is, what a function inverse is usually we talk about plugging an x into a function and getting a y out. Right? That's usually how we think about functions, which is what's being shown right here. Right? Usually we plug an x into a function and we get out a y. The inverse function does the opposite. It takes the y values and sends them back to the x values that they came from. And so that's why it's called the inverse, right? Inverse means kind of like opposite in some sense, right? But if we're going to send the y values back to the x values they came from, we need to only have one x value that it came from. And so that's why we need to have a one-to-one function. And so only one-to-one functions have inverses because of that reason. If we want to send the y value back to the x, there can only be one x that it came from. And that's what's being shown in this picture here. So if A is the domain and B is the range, right? We got our classic bean pictures here. The function itself takes x values from the domain and sends them to y values in the range. That's how we usually think about functions, right? But this is showing us that the inverse takes the y value and sends it back to the x. And so let's write that down right here. So inverse functions send y values back to the x values from which they came. And so that's what we're thinking about when we're talking about inverses. Conceptual questions about that yet? Do you see why we need to have a one-to-one function? Remember, if something's not one-to-one, that means that x values are associated with more than one y. And so we need to know where to send them back to. I'm sorry, I said that wrong. If it's not one-to-one, that means that there's more than one y that's associated with, let me start over. One-to-one functions means that there are y values that are associated with more than one x. And so if y values are associated with more than one x, we don't know where to send those y values back to. So we need to have a one-to-one function. And so that's what it says right here. I'm going to star that. We need to have a one-to-one function in order to have an inverse. So keep that in mind. And the other thing is, notice the notation here. See how the inverse, this is the inverse function, and it's got like a -1 exponent. But that's just a notation thing. The notation just means that it's sending the y values back to the x. In other words, it's not really an exponent. I know it looks like an exponent and it's in the exponent spot, but this does not equal this, right? We cannot treat this like an exponent. So in other words, the minus 1 in f to the minus 1 is not an exponent. It just means inverse. It's just notation that means inverse. I know that's a little confusing because it looks like an exponent, but that's why I'm just trying to say that out loud, because it's not. It just means inverse. And so I say that, I usually pronounce that f inverse, or inverse of f, or the inverse function, or something like that. But I won't call it f to the minus 1, because f to the minus 1 kind of makes it sound like an exponent, right? And it's not an exponent. Is that okay? So here are some kind of practical applications of what this looks like. So what's being shown in the boxes here is also being represented in the graphs below. And so this box says f of 1 is 5. So in other words, f takes 1 from the domain and sends it to 5 in the range, right? F of 3 is 7. It sends 3 to 7. It sends 8 to minus 10. The inverse sends them back. And so notice how this is, you can see that this is an x value and this is a y value, right? Well, in the other sense, we're taking the y values and we're sending them back to the x's, right? So if f of 1 is 5, then f inverse of 5 is 1, right? The inverse is just taking the things in the range and sending them back to the domain, right? And so this one on the left is the f, and the one on the right is f inverse, and they're going in opposite directions. So like, for example, down here, if f of 26 is 109, right, so this is my x and this is my y, then what is f of 109? So y value, it's in the range. Where does it get sent back to? 26, right? Yeah, it just gets reversed. It's sort of a straightforward kind of concept, right? What about this one? If f of minus 12 equals 29, then what's f inverse of 29? Oops, sorry. Just sends it back. Say it out loud. Minus 12. And so you'll see problems a lot that look like this. It gives you the function value and the output, and then it wants to know where the inverse gets sent back to. I also just want to mention, sometimes you might see one like this, which is the opposite. Like, it might tell you the inverse first, right? It's saying the inverse, and so this is like a y value and an x value. And so then we would say, what's f of 1? You just reverse it again. Right? So if f of inverse of 2 is 1, then f of 1 is 2. Good. Okay, so that's a pretty straightforward relationship. I think, I don't know, let me know. Is that okay? So the point of this page is just to kind of get the concept and get some simple problems out of the way. And you'll see some simple problems like this in the homework. They're fairly straightforward. Okay, great. So let's look at the next page, because ultimately what we want to do is we want to start with the function and then find that function's inverse. So that's what we're building towards, and we've got the conceptual stuff out of the way on this one page. Is everyone else set with this page? Okay. So let's look at this property here. It's called the inverse function property. And let's see what it says. So let f be a one-to-one function. We need it to be one-to-one because we're going to talk about an inverse in a second. And so we need one-to-one functions to have inverses with domain A and range B. We say that the inverse function satisfies the following cancellation properties. What does this look like? First of all, it looks like we're plugging a function into another function in both of those situations. What is that called? That was from one of the previous sections. Yeah, good. It's a composite function. Right, we see this composite function, so I'm just kind of linking it to a previous section. This is just a composite function where we have one value, one function plugged into another one, right? And you can see in the first line, we have the original function plugged into the inverse. And in the second line, we have the inverse plugged into the function. right? They're opposites of each other. But in both cases, what happens is everything cancels out and we just get x back out. And so we have this interesting property that says when we plug the inverse into the function or the function into the inverse, either one of those, everything cancels out and we just get x out. And so practically speaking, look at the first one. If the inverse sends y values back to x, f of x are y values, and it's sending them back to x values. So this is literally another representation of what an inverse is, right? It's taking y values and sending them back to x values. But the way we usually use this is to check our answers. This is a good way to check to see if two functions are each other's inverse. Because if they are, you can plug one into the other one, and everything should cancel out, and you should get x out. And if it doesn't, then they're not each other's inverse, right? So let's look at one example of that. So we've got our two functions. I've got two functions here, f of x and g of x. And let's verify that they are each other's inverse. And so let's plug them into each other and see if everything cancels out and we get x. So I'm going to plug g into f and see what happens. And then I'm going to plug f into g and see what happens. Right? And we know this notation. This is just the composite function notation. And ultimately what we'll do is we'll do some algebra, ... and if we get an x out, if it simplifies into just x, then that's an indication that we have that they are each other's inverse. So let's do the first one. G plugged into f looks like this. We take this x to the 5 halves, and we're going to put it into this x, right? And so it'll be x to the 5 halves raised to the 2/5. That's what f of g looks like. Is that part okay? So that's from the composite function section, right? And now it's an exponents problem. We have an exponent raised to an exponent. What do you do in that situation? Yeah, we multiply those things. So we get 5 halves times 2/5. And when we multiply fractions, we just multiply straight across the top. And so we get x to the 10 over 10, which is x to the 1, which is x. And so that's a good indication. We plug one function into the other one, and things simplified down to just x. And so it's meeting, so far, it's meeting this inverse function property. And quite frankly, if it works with one of them, it's going to work with the other one. But we'll do the other one just to be sure. But that's a good indication so far. But we'll see the same thing happens when we plug f into g, right? So plugging f into g means taking this x to the 2/5 and plugging it into this x raised to the 5 halves. And so we'll get x to the 2/5 raised to the 5 halves. And we end up doing the same thing, right? We end up multiplying those things together. And we end up getting x to the 10 over 10, which is x to the 1, which is x. And so this is an indication, this is proof that these are each other's inverse, right? So since we plug them into each other, so f of g of x equals g of f of x, and it equals x, that means that by the inverse function property, f and g are each other's inverse. Questions about that? We'll try another. We're going to do that again in just a second. This is a particularly boring example too, because it's just like one x and you plug it into the other x. It's not particularly exciting, but I just wanted to show you how that works in a kind of a simple example. And we'll do it again with this next one down here. Are there any questions first? Okay, so how do we solve for an inverse? That's what I really want to talk about. That's the important thing. Okay, so here are the steps to solving for an inverse. the first thing is you write y equals whatever the function is. And so this is going to be an expression that has y in terms of x. So y is going to be on one side and x's are going to be on the other, just like this first example. And then what you do is you solve the equation for x in terms of y, if possible. If it's not possible, there's no inverse. So be aware, there might not be an inverse. For example, what would make something not have an inverse? What's the condition on having an inverse? Let's start there. Yeah, we need it to be 1-to-1. So if we have not a 1-to-1 function, it's not going to be there's not going to be an inverse, unless we restrict the domain. But anyway, we'll get to that later. And then once we have, so we start with something that says y equals. We get it so that it says x equals, and then you switch the x's and the y's, and you have your inverse function. So let's look at a simple example. This one's sort of a simple example because it's just a linear equation, and so it's not too tough to solve for x. And then we'll use the inverse function property. So I would draw a line somewhere in here, like way over on the left. And we're going to use part of the page to do the inverse, and then we'll use the rest of the page to test it out. And so let's find the inverse. And I'm going to follow these steps, 1, 2, and 3. And I'm going to write them down, 1, 2, and 3. So the first step is to write y equals your function. So our function is 5x plus 10. So we have y equals 5x plus 10. Step 2 says solve for x. And so let's get x by itself. And so I'm going to subtract the 10 over to the other side first. And then I'm going to divide by 5. And we solve for x. And so right off the bat, I'll let you write that down, so I'd like you to look up here and look at this here. The original function, if you look up here, we plug in a x and we get out a y. And in this function, we plug in a y and we get out an x. And so this is, right, the original function is the original, and then this one down here that we just solved for is the inverse because it's taking the y values and sending them back to the x values. And then step 3 is to switch the x and the y. And we usually just do that. I always go back and forth about whether or not I like this step. We just do that because usually when we talk about functions, we think about plugging x values in. But what we just found is a pretty good version of the inverse. But just in case, sometimes you want to switch the x and the y, and you'll see that in the, you'll need to do that for the homework. And so when you switch the x's and the y's, we get f inverse of x equals x minus 10 over 5. And so it's just two different versions of the same equation, right? The first one is the inverse with a y in it, and the second one is an inverse, but we just changed the variable to x. And so they're the same thing essentially. They just have a different variable depending on what the context is, really. Great. Questions? So what I want to do with the rest of this page, or the rest of the page here, is let's use the inverse function property and check our work. So use the inverse function property to check our answer. And so in order to check the answer, we plug each function into the other function, and we see whether or not they cancel out when we get x, right? We're going to do both these things just like we did in this previous problem. And so what I'm going to do is I'm going to take my function, or my inverse, and plug it into the function. And I'm going to do the opposite. I'm going to take my function and plug it into the inverse. And I'd like you to actually do that and see what you get. All right, so this is the inverse right here. And so this first step is taking the inverse and plugging it into that function. And the second one is taking the original 5x plus 10. I'm sorry, I pointed at the wrong thing. The first one is taking the inverse, which is x minus 10 over 5, and plugging it into the original. So it's plugging it into this x. Right? And then the second one is taking our original function 5x plus 10 and plugging it into the inverse. So taking the 5x plus 10 and putting it into there. All right, see if that works out. It should cancel down to x. We did this one right, and so it should cancel. And if you're still confused, I'll just write the first step down. So that's plugging the inverse into the function. Oops, plus 10. And then plugging the function into the inverse would look like this. All right, take a minute and simplify that down. Everything should cancel, and we should just get x out. Give that one a try. Did you get x out when you do that? I think it should work. So on this first one, the first thing that happens are the 5s cancel, right? So the 5 in the denominator cancels with the 5 multiplying it, and we end up with x minus 10 plus 10. And then the 10s cancel, right? And we just get x. So that's what we were looking for. That's good. And then the second one, the first thing that happens are the 10s cancel. And so we get 5x over 5. And then the 5s cancel, and we just get x. And so it worked, right? So the first one worked, check. Second one worked, check. And so what we can say is, since f of f inverse of x equals f inverse of f of x, and they both equal x, right? They all equal each other and they all equal x. That means that we have indeed found the inverse. Questions about that? Thoughts about that? Comments about that? Okay, that's good and fine, but this, like I said, this is about as easy as an equation can be in terms of finding an inverse, because there's only one power of x, there's no fractions or radicals or anything, and so this is about as straightforward as it gets. So we want to look at something a little more complicated. Yep.
Can you show us an example, like step 2, where we solve the equation for x in terms of y when it's not, when it's impossible?
Sure. So the question is, can we come up with an example where we won't be able to solve x in terms of y? So how about I have a hard time thinking off the top of my head here. Let me write a little scratch work. Give me 1 second. Well, that's kind of a cheap one. Yeah, that works though. So let me think of a function that's not 1-to-1. Right, so how about just y equals x squared? That's a real simple one, where if we try to solve for x, what do? we take a square root. And so we'd get plus or minus square root of y equals x. And so x equals positive y and x equals negative square root of y. And so we can't explicitly solve x for y because we get two separate equations in that situation. We want to just have one equation that says y or x equals, and we ended up with two. There are other, I'm just not be able to think of one off the top of my head where it's not possible to do both. How about
Does it only work when the power of x is 1?
so we need odd powers to have one-to-one functions. That is true. But there are other situations where we could not solve for x, and just I'm having a hard time just coming up with one. Did you have one, or do you want to add something, Tom? Did you have a question? Just waving?
Yeah.
Cool. Yeah, I can't think of one off the top of my head. I'm sorry. You'll see one in the homework, though, if that helps. Does this one work? I might have one. No, that doesn't work. So this is another one, maybe. We had one like this. We wouldn't be able to solve for x on that one, so if we cross multiplied, we'd get yx minus y equals x squared. Is that right? And again, you'll see the same thing where we end up with a square. So this, if we try to get the x's by itself now, we would get yx minus x squared equals y. And then how are we going to isolate the x here? We can't. Like, I want to factor an x out, but one's got an x and one's got an x squared. And so this is a situation where we can't isolate the x. So this is another, that's an example. Usually it happens with fractions. Sometimes it happens with fractions. Yeah, good thought though. So it is possible for them not to have one an inverse, which again usually just means it's either not a function or it's not one-to-one. Let's look at a more complicated one though, because like I said, we want to be able to solve more complicated inverses like this one, like a fraction, right? And so if the function is a rational function, what does rational function mean again? That was one of the sections. What does that mean? On the next test next Wednesday, what is a rational function? It's a fraction. So if we have a function that's a fraction, like the one that's shown right here, then how do we get rid of denominators? This is a great throwback to the rational function section because this is on the test, right? How do we get rid of denominators? If we want to clear denominators out of something and not end up with fractions, what do we do?
Multiply each side by the top.
Yeah, we multiply by the denominator. Great. And so I think I actually wrote that here. Yeah, so if the function's a fraction, you have to multiply both sides of the equation by the denominator. And then you carry out any distribution, and you isolate x. And there's an important note here that says you may need to do some factoring in order to isolate the x variable. Like this, in that non-example, this one. I really wanted to factor this out, but I wasn't able to factor it. So that's what tripped me up on this one. But usually you are able to do that. And I know I wrote you may need to do this, but I'm just going to go ahead and say you almost always need to do that. You usually do need to do that, and you'll see that in this example. So let's go through the steps again. So the first step on the last page said write y equals. So let's write y equals x minus 2 over x plus 2. And then step 2 is to solve for x. And so, as we just pointed out, that means multiplying by the common denominator, or the denominator in this case, right? And so we multiply both sides by the denominator, and we get x plus 2 times y equals, I'll just write out the details, x minus 2 over x plus 2 times x plus 2. Right, and so the whole point of doing that, as we just mentioned, is so we can cancel out the denominator. The x plus 2's cancel. And so we don't have a fraction anymore, that's good. And then we distribute the y. And so we'll get xy plus 2y equals x minus 2. And now this is where my factoring note comes in. We need to get the x's on the same side, and then we factor. And so what I'll write here is we group the x's on the same side. I'm going to do that in one step here. Let me write the step down and then let me know if it makes sense. So I got all the x's over to one side, and I got everything that's not an x over to the other side. And so I usually get at least a little bit of confusion related to this, which is what I did was I brought this x over to the other side by subtracting it, right? That's why I have the minus x here. So I have xy minus x. And then I moved the 2y over to the other side by subtracting it. So that's why I have the minus 2 and the minus 2y over on the other side. So okay, I just did 2 algebra moves just in one, didn't write them down. Just want to make sure that that's okay. But the point is, now the x's are on one side and the not x's are on the other. And this is where we want to factor, because we've got a common factor here. So we can factor out an x. And so let's do that right here. We factor an x out, and we get that. Why did we want to do that? How did that help us? What was the point of factoring this x out of that left-hand side? Like, what's the next move here that's going to help us isolate the x? What do you think, Andrew?
Divide by y minus 1.
Yeah, nice. We can divide by y minus 1 to cancel it off the left side, and then we're just left with x, which is what we wanted, right? And then the other side will be minus 2y minus 2 over y minus 1. And so again, like we started with something that said y equals, and so that outputs y's, right? It input x's and outputs y's. And we ended with something that says x equals, and so that inputs y's and outputs x's, which is exactly what we were looking for. And then if we want to write down the inverse in terms of x, we just switch x and y. And so we could get f inverse of x is minus 2y minus 2 over y minus 1. Oh, thank you. Yeah. I said switch the x's and y's, and I didn't do it. Those should be x's, thanks. Questions about that? Were you thinking about pulling a 2 out? You could factor and pull a 2 out of the numerator if you want to, but it's not necessary. Oh, you're thinking like something might cancel? So if we pull a 2 out, it won't cancel because we'll end up with minus x minus 1 instead of x minus 1. So you can't cancel those two because that one's got the minus sign. But good thought. Yeah, that's a good thought. If you could cancel, that would be a good thing to do. Otherwise, they're the same answer, so it's fine. Other questions? So let's look at what this looks like visually. I like this last thing. I always like to try to bring it back to something that we can look at and see and visualize. And so maybe let's look at the graph first. So in this graph, what's being graphed here is the graph square root of x minus 2. So this is our f. This is our f of x. And then the inverse of square root of x minus 2 is being graphed right here in the red, f inverse of x. And so you can see that the function takes x values and sends them to y. And this is interesting because it's kind of like it takes y values and then it sends them back to the x. And the way we obtain, if we wanted to just obtain this graph of the inverse from the original, it's what it says in this box here. The graph of the inverse is obtained by reflecting the graph of the original function about the line y equals x. And so you can see in the middle here is the line y equals x. And so it's kind of like if we took, if you look up here, I'm going to do something with my hand. If we took this square root graph and we flipped it around the line like that, so we just kind of like flipped it over the line like that, it would line up with the inverse, right? Or the other way to think about that is if we folded this page along that line, those two things would line up with each other, right? And so that's the interesting thing, is because we're sending y values back to x, so if we flip it over the line y equals x, we actually get the inverse. It's like an interesting little property there. So let's just look at one real quick. So let's say our original function is x cubed. We looked at that one a couple times yesterday, right? That's this thing. And so let's solve for the inverse. So we write y equals. We want to get x by itself. How do we get rid of a cubed? Cube root. And so we do the cube root of y equals x. And so that means that the inverse is the cube root of x. And so we got our inverse, and we've got our original here. And let's graph them. So if I graph, let's see, I'll draw my axes like this. If we graph cube root, we did that twice last time, right? Cube root looks like, or I'm sorry, x cubed looks like this. And then the cube root looks like this. And so you can see, like, and let me draw in the line y equals x. The line y equals x just diagonally goes through here like that, and it diagonally goes through here like that. And, you know, forgive my small handwriting errors and all that stuff. But if we reflect the graph on the left, if we reflect around the line y equals x, and again, that's what's being shown in the red here. That's y equals x, y equals x. If we, and I'm doing something with my fingers here again, if we took this graph on the left and we just flipped it over like this around that line, it's kind of hard to imagine, but it would look like this, right? Like this thing, if we flipped it over that line, it would end up pointing that way, which is what this one does. And if we turned this one around that line, it would end up pointing that way, which is what this one does. And so we kind of think about reflecting around that line. Again, it's kind of like this thing, right, around that line. Yeah?
So just like, so say like, you know, like the points of the function, like know, like all, like a good amount of the points would like making the inverse points just basically flipping the line next. Like, so like negative, like say there's a point that's like -2 and 3, would the inverse be 3 and -2?
Yeah, exactly. So if we had the question was, if we had the points, this is just an aside that has nothing to do with this. If we had the points -3, 2, sorry, that's supposed to be 2, on our graph for f, then the point 2, -3 would be on our graph for f inverse. Absolutely. Yep. Yep. And that's what's going on with all these points. Like this point, if we flipped whatever that point is around, it would be that point. And vice versa, right? So we can just flip all the points, and that's how we end up doing that. And again, that's why we flip it around the line y equals x, because of exactly what Jason just said. I always want to call him Josh. I don't know why. Right? We're literally letting y equal x when we do this. This is an x and this is a y. And when we let y equal x and vice versa, we get this. So that's why we flip it around that line, because we're just flipping those things. Yeah?
So essentially, like when you do the inverse, it's basically like having the x being the y-axis. Because like if you take that and flip it, it'd be basically like x being y, and then Y.
Yes, that's right. You flip the x and the y, exactly. But just to be clear about that, you don't just start with your original equation and switch the variables, right? That's different. We want to solve for x. But if we have points, then yes, you can just flip the x's and the y's. Absolutely. And so this is sometimes useful just because if you get a graph of f, you already know what the graph of f inverse looks like. Or you might see in the homework, it might say like, are these two each other's inverse? Or it might give you the graph of f and say, match it up with the graph of f inverse. And you just want to think about flipping it over the line y equals x. That's how you think about those. Other questions? All right, that's all I've got for today.